Hello, and welcome to my talk on broadcast in generalized network and adversarial models. This is a joint work with Chen-Da and Ueli Maurer at ETH Zurich. We'll start with the usual setting of a Byzantine fault model, namely, we have n parties using a communication network, and some parties could be corrupted, shown in red here. We model this corruption by assuming there is an external adversary that has complete control over such subsets of parties. And a specific party known as a sender would like to broadcast its input value V to all other parties such that if the sender is honest, then all other honest parties end up with the same output value V. And if the sender is corrupted, then we would like to guarantee that at least all the other honest parties agree on some common output value V prime. Now let's focus on different types of communication networks. A seminal result by Pias et al. States that in a classical model of communication, where we have bilateral channels between every pair of parties, broadcast is possible if and only if the maximum number of corrupted parties, denoted by T here, is less than n-third. Now one may ask, is it possible to tolerate more corruptions? It turns out that it is possible, but if we assume some stronger communication primitives in the network. To be specific, Considine et al. Showed that in the so-called B minicast model, where in addition to these bilateral channels, if we have some partial broadcast channels between every subset of B parties, then broadcast is achievable if and only if the T is less than the specific fraction of n. So here we have a 3 minicast model where there is a 3 minicast channel between every triplet of parties. Now, such 3 minicast channels allows the party to locally broadcast its value to the other two. And in this setting, if we set b equals 3, then we can already tolerate corruptions up to n-half. Now, looking at the previous two results, a natural question would be to know the trade-off between the strength of the underlying communication network and the strength of the adversary that can be tolerated. Looking at some related work, we have already seen the bounds on the number of corrupted parties that can be tolerated in the classical model and the B minicast model, respectively. So one thing to note here is that until now, we have been looking at some specific kind of adversaries that are characterized by a threshold number of parties or a maximum number of parties that can be corrupted by them. But we can actually go ahead and talk about a very general form of adversaries that are only characterized by the subsets of parties that can be corrupted by them. So for example, the adversary A can either corrupt a subset A1 of parties or a subset A2, and so on. And it was shown by Raykov that broadcast is possible in the B minicast model and against a general adversary if the adversary satisfies the so-called B+1 chain-free condition. We will be seeing shortly what this chain condition actually is, but it is something that is quite important in the rest of this presentation. And one issue with these results is that they assume complete network structures. That is, for example, in the B minicast model, we assume there is a B minicast channel among every subset of B parties. And in our work, we are interested in communication models that need not be complete. That is, only certain subsets of minicast channels can be available in the network. At the same time, we're also interested in broadcast that is secure against these general form of adversaries. Now, looking at some related work, the broadcast problem has already been studied for general 3 minicast networks and with respect to these specific threshold adversaries in this range, because if T is less than n-third, then we know that broadcast is already possible in the classical model with bilateral channels. At the same time, if T is greater than or equal to n-half, then we know that broadcast is not even possible even if we have a complete 3 minicast model. Similarly, in our work, we focus on general B minicast networks and at the same time, general adversaries in this range, that is, adversaries which contain a B chain and which are B+1 chain free. It will become clear shortly why we chose this class of adversaries. Now, just to give a taste of our results, let's look at a very simple example. Let's consider a complete 3-mini-cached model among 6 parties, and there is a threshold adversary that can corrupt up to 3 parties. In this setting, we know that broadcast is impossible, thanks to this result by Considine et al. So if we plug in the parameters, setting b equals 3 and n equals 6, then we can see this indeed the case that broadcast is impossible. Now, at the same time, if we upgrade our network to a complete 4-mini-cached model, then broadcast becomes possible. But what if, from a complete 4-mini-cached model, certain 4-mini-cached channels are missing in the network? Specifically, if this particular 4-mini-cached channel were to be missing, this particular 4-mini-cached channel, this channel, and this channel. So if these 4-mini-cached channels are missing in the network, then in our work, we show that broadcast again becomes impossible for the same adversary. Now, fixing this incomplete 4-mini-cached network, now if we look at some weak adversaries, namely, instead of an adversary being able to corrupt any subset of 3 parties, the adversary it can only corrupt certain subsets of 3 parties. Namely, the adversary can corrupt either this subset, this subset, this subset, or this subset. So if the adversary is now restricted to only corrupt these subsets of 3 parties, then we again show that broadcast is possible in this incomplete 4-mini-cached network. On a high level, this is what we are doing. So to analyze this broadcast problem in general networks, we first partition the space of all possible general adversaries in the following classes in an increasing order of strength. So here, the weakest class is U0, which contains adversaries that are 3-chain free. They're considered to be the weakest because broadcast is already possible in the classical model of communication with bilateral channels. And subsequent classes are defined as follows. So adversaries which contain a B chain and which are B+1 chain free. So once we have an ordering on the adversaries, we can also have some kind of ordering for the communication models as well. So the weakest class is, of course, the classical model of communication, where we only have bilateral channels. Now we can make this model stronger by adding some 3-mini-cached channels on top of it. So in this region would be the incomplete 3-mini-cached networks. And once we have a 3-mini-cached channel for every triplet of parties, then we have our usual 3-mini-cached model. And we can repeat the process for 4-mini-cached channels, for 5-mini-cached channels, and so on. And now for each of these classes of adversaries, say for this general class UB, since the adversary contains B chain, we know that broadcast is impossible in the B-1 mini-cached model, thanks to Raykov's result. And by extension, broadcast should be impossible in the weaker models to the left. At the same time, since this class of adversaries do not contain a B+1 chain, broadcast is possible in the complete B-mini-cached model, and hence broadcast is also possible in the stronger communication model to the right as well. So this much was known from prior work. And in our paper, one of our contributions was to bridge this gap. Specifically, for a general class UB, we show that broadcast is impossible in certain incomplete B-mini-cached networks in this region. And we also have some positive results. Namely, we first identified some weak adversaries in each class, and against them, we showed that broadcast is achievable in networks that need not be complete. That is where certain B-mini-cached channels are missing. Now let's look at these chain conditions. So what do we mean when we say a general adversary A contains a B chain? So this is again a usual form of a general adversary in terms of the subsets of parties that can be corrupted. Now, before talking about a B chain, let's look at a simple example of a 6 chain. So we say that an adversary contains a 6 chain if there exists a partition of the n parties into 6 non-empty subsets, such that leaving any 2 adjacent sets, the adversary can corrupt the rest. So in this case, the adversary, say an adversary can corrupt the union of these 4 subsets, Let's call it A1. Let's say this is A2, A3, A4, A5, and A6. So if the adversary can corrupt these subsets of parties, then it is said to contain a 6 chain, where the 6 chain is again described by the partition S1, S2, and so on until S6. And we say that an adversary does not contain a 6 chain if this property does not hold. And the definition for a B chain, it generalizes in a straightforward manner. Now, after describing these chain conditions, we will now come to one of our main results. Namely, we characterized certain minicast channels to be essential for broadcast. To give an intuition, let's start with a result of Raykov, which states that in a smaller setting with B parties, and if we are in a complete B-1 minicast model, then broadcast is impossible if the adversary contains a B chain. And the key idea that we used is to extend this impossibility result from a complete B-1 minicast model to an incomplete B minicast model. And to illustrate this idea, let's start with an example with 4 parties and in a complete 3 minicast model. So, and the adversary here contains a 4 chain described by S1, S2, S3, and S4. In the setting, we know that broadcast is impossible. Now let's look at another setting with 6 parties and in an incomplete 4 minicast network. Now we'll be seeing in a moment which minicast channels are actually missing in the network. And let's say an adversary in this case also contains a 4 chain described by S1 prime, S2 prime, S3 prime, and S4 prime. And now the network is nothing but the complete 4 minicast model, but with certain 4 minicast channels missing. And the 4 minicast channels that are missing are of the form which with their endpoints in each of these partition sets. That is, we will be removing this particular 4 minicast channel from the network, this particular 4 minicast channel, this channel, and this channel. So from the network, we are removing 4 minicast channels. And then we can show that broadcast becomes impossible in this setting as well. And we show this via a reduction. Namely, if broadcast is somehow possible in this case, then broadcast should also be possible in this case, which leads to a contradiction of Raykov's result. Specifically, let's say that the broadcast is possible by this sender, then broadcast should also be possible by this sender in this setting, where S1 would be simulating the pair of parties S1 prime, S2 would be simulating S2 prime, S3 would be simulating S3 prime, and S4 would be simulating S4 prime. And now S1 would just run the broadcast protocol used by this party in this case. And one key thing to note here is that in this incomplete network, all possible 4 minicast channels could be simulated. For example, if we have this 4 minicast channel shared by parties from S1 prime, S3 prime, and S4 prime, it can be simulated by the 3 minicast channel shared by S1, S3, and S4. But if we go back to the 4 minicast channel that we have removed from the network, which had its endpoints in S1 prime, S2 prime, S3 prime, and S4 prime, then this could only be simulated if there was a 4 minicast channel among S1, S2, S3, and S4. But we don't have 4 minicast channels in a 3 minicast model. Hence, in a way, these particular 4 minicast channels that we have removed are essential for broadcast, because if they are not present in the network, then broadcast becomes impossible. And this brings us to our necessary condition on general networks for broadcast to be achievable against general adversaries. So we say that broadcast is achievable in a general network and against an adversary in the class UB only if for every B chain contained in A, which is described by the partition S1, S2, and so on SD, recall that adversaries in the class UB contain B chains. So for every B chain, there must exist a corresponding B minicast channel in the network that is shared by a party from S1, a party from S2, and so on, and a party from SB. So these B minicast channels of this form are nothing but the essential minicast channels that we have identified previously. So if such channels are missing from the network, their broadcast becomes impossible. So here we are currently restricted to B minicast channels, but we can actually prove something stronger with respect to the underlying minicast channels as well. More concretely, not only B chains, but for every K chain in A, where K ranges from 3 to B, of the form S1, S2, and so on, Sk. So we say, so broadcast is possible only if there exists a corresponding K minicast channel in the network, which is shared by a party from S1, a party from S2, and so on, and a party from Sk. And after characterizing our necessary condition, we also provide some sufficient conditions on general networks for broadcast to be achievable against general adversaries. Again, before stating the result, we first give some intuition towards it. So let's start with a result of Rakov, where broadcast is possible in the complete B minicast model among n parties if the adversary is B chain free. And in our work, we extend this positive result to a general B minicast network, which could be incomplete, where some B minicast channels could be missing. So we want to apply Rakov's broadcast protocol in a possibly incomplete B minicast network. But the problem is, such a protocol requires a complete B minicast model to begin with. So our key idea was to start with an incomplete B minicast network and to recreate a complete B minicast model. And we do that by simulating the missing B minicast channels with Rakov's protocol. That is, we apply Rakov's protocol in a local setting among B parties to patch these missing B minicast channels. So we'll make this idea more clear using an example shortly. But we call such B minicast channels, which could be simulated by us, as non-essential B minicast channels. That is, whose presence is really not required in the network for broadcast to be achievable. Now, to illustrate the simulation idea, let's look at an example among 6 parties. So we make an assumption where the underlying network has a complete set of 3 minicast channels. And now Rakov's result states that if we have B parties in a complete B-1 minicast model, then broadcast is possible if the adversary is B chain free. So in our example, if we focus on these 4 parties, then these parties can simulate a 4 minicast channel among themselves, since they lie on a network where we have a complete set of 3 minicast channels. So if the adversary is 4 chain free, then a virtual 4 minicast channel can be simulated. But we have to be a bit precise when talking about an adversary, because in this case, an adversary is defined with respect to these 6 parties. But what we actually require is the adversary should be B chain free if its corruption power is locally restricted to these 4 parties only. To make this notion more precise, so let's start with the usual characterization of a general adversary, characterized by the subsets of parties that can be corrupted by it. And we define a new adversary structure called A row, which is nothing but the projection of A onto a subset of parties rho. And A of rho, it contains, it's a set that contains the intersection of all of these sets that could be corrupted with rho. So in our example, if we have rho to be the set of these 4 parties, and if the original adversary A could corrupt the set of these 3 parties, so if this is A1, then corresponding to A1, A of rho could corrupt these 2 parties, since we don't really care about this party and this party. And this brings us to our sufficient condition. Namely, broadcast is achievable in a network with respect to any sender while tolerating a general adversary in the class UB. If, first of all, there should be a complete set of B- and minicast channels in the network. Recall that this was our starting assumption in order to use the simulation idea. And for each subset of B parties, the adversary's projection on these B parties, if it contains a B chain, then there should be a B minicast channel among rho. Now, if A of rho did not contain a B chain, then we didn't really require a B minicast channel among row because it was non-essential. So it is sufficient to only have B minicast channels, in the network, except ones that are non-essential, in order for global broadcast to be achievable. But again, we can prove something stronger. So we can use this simulation argument recursively among the lower minicast channels as well. That is, we can use a bottom-up approach. So we first required the network to only contain a complete set of bilateral channels. Then we start with k equals 3. So for each subset of 3 parties, we identify the set of non-essential 3 minicast channels. So then it is sufficient to just have the other 3 minicast channels to be present in the network. Then we move on to subset of 4 parties and so on. Now note that this sufficient condition would be trivial if it required all B minicast channels to be present in the network, because then the condition is not really helpful to us and we are back in the case of a complete B minicast model. And in our work, we showed that this condition is non-trivial for certain weak adversaries in the class UB, which we call B-chain adversaries. So if we revisit the hierarchy of adversaries that you have seen, so recall that the class UB contains adversaries which contain a B chain and which are B+1 chain free. Now, so these weak class of adversaries called B chain adversaries, they just contain a single B chain and nothing more. That is, these adversaries, they minimally satisfy this requirement to be considered as a part of UB. And we showed that with respect to these B chain adversaries, there do exist B minicast channels that are non-essential. So in this sense, the sufficiency condition is non-trivial for these adversaries. So coming to some of our other results that I couldn't cover in this presentation. So our conditions, they actually allow us to derive separate bounds on the number of B minicast channels that are necessary and that suffice in achieving global broadcast in general networks secure against general adversaries. Now, Yaffe et al., they provided such tight bounds on the number of 3 minicast channels in a network. And in our work, we could extend their analysis to general B minicast networks, although our bounds are non-tight. And this brings us to an important open problem, namely to come up with tight, necessary, and sufficient conditions the general networks need to satisfy in order to realize secure broadcast against general adversaries. So our conditions are unfortunately non-tight, but we hope that our results, they provide some starting steps in this direction. So in fact, for general 3 minicast networks, tight, necessary, and sufficient conditions were already derived by Ravikant et al., where they used a technique called virtual party emulation. And in our work, we showed that a straightforward extension of this technique cannot be applied to a general B minicast setting. Another interesting open problem would be to study the practical implications of our results or subsequent results on the achievability of broadcast in general networks that is secure against general adversaries. With this, I conclude my talk. Thank you.